Okay.
All right. Well, good morning, good afternoon, and good evening from wherever you are in this world. And which, by the way, if you have a chance to let us know where you're from, where you're. And then, so we have here Eric from New Hampshire. Um, we have here John from the San Francisco area. And I'm from Flemington, New Jersey. So if you get a chance, please let us know. Um, I'm happy to introduce Mario Fusco. He is a senior principal software engineer and the Drools project lead at Red Hat. Red Hat. That was weird. And this is day 4, session 1. It's been for me. It's been a pleasure moderating all these a number of these sessions. So with that, I'm going to disappear. Oh, let's just we'll show here. Sebastian Bergel is from Germany. So, all right. So with that, take it away, Mario.
Okay. Thanks a lot. So, hi all, and thank you for joining me in this session. My name is Mario Fusco. I'm from Italy, and I work for Red Hat. This session is supposed to be actually the continuation of what of the one I had last year, meaning that I started doing some experiment with virtual threads at time, and now that we have Java 21, virtual threads are finally generally available with the JDK, and in the meanwhile I continued with my experiment. So the idea of this talk is to show the result of this experiment, my experience in the last year using virtual threads into the wild, and a few epiphany, a few gotcha that I had while using them, for good or bad. Okay, so I will give mostly for granted that you know what virtual threads are, but I will do a quick recap of what they are. Okay, so before having virtual thread, we had the Java regular native thread. Um, the thing for which they are a scarce, the reason why they are a scarce resource is that the Java threads are the native one are a one-to-one match with the threads provided by the operating system. Okay, so the idea of virtual thread is to overcome this limitation by multiplexing one on one native thread that in this case is called the carrier of the virtual thread, multiple virtual threads. So in essence, in this way, we can run many virtual threads at the same time. And the reason why we are doing this again is, first of all, because the native thread are a scarce and an expensive resource. But the main reason is that we want to use this resource in a efficient way. Okay, so the problem is that when we write a blocking code and we are blocking a native thread, we are make unavailable a resource, a scarce resource, a resource that is expensive, a resource that we don't want to waste. Okay, virtual thread instead are a very cheap resource. They are very quick to be created, and in fact, there is no reason to pull them, for instance. And the fact is that when we do a blocking operation on a virtual thread instead, what happens is that you are simply blocking the virtual thread, but in that case, the virtual thread is unmounted from the carrier, and then another virtual thread can be mounted on the same carrier and do some job. And when the blocking call is terminated, the virtual thread can be resumed and mounted on that carrier or a different one. Typically, this carrier thread come from a dedicated fork join pool. In essence, you have a number of carrier thread that is by default equal to the number of the cores of your machine. Okay, so for instance, I'm having a 8-core machine here, so I have a virtual thread pool, carrier pool made of 8 native thread, and the virtual thread compete to take the carrier and do some job on the carrier. Okay, so in essence, the main point of virtual thread is that they can perform a blocking operation without wasting resources. So in essence, the things on which virtual threads really shine are simply waiting. Okay, and there are a few reasons why I'm saying that virtual threads are much more lighter than the native one. First of all, the metadata taken from a native thread is typically in the range of 2 to 3 kilobytes, while for virtual thread is 10 times less. Okay, but this is just a minimal difference compared to the memory that we save for what regard the stack. The difference here is that when you create a native thread, the Java virtual machine actually allocate an area that is typically big around 1 megabyte for the stack of that native thread. And regardless or not, if you use, regardless of the depth of the stack used by the native thread, you are using 1 megabyte. Okay, so this is one of the reasons why you cannot have many threads, because at that point you will saturate the memory with the stack of the native threads. Okay. Conversely, for what regards the virtual thread, the stack is a data structure that grows and shrinks based on how many calls you have on the stack. Okay, so it's a pay-as-you-go data structure. Nothing is pre-allocated. And the last but equally important characteristic of virtual thread is that when you do a context switch of native thread, this is something that happens. Again, the native threads are only a tiny wrapper around the operating system thread. So when you do a context switch with native thread, this is something that happens in kernel space. When you do this for virtual thread, is something that happens in user space. So even here is generally around 10 times faster. Okay, so with all this notion, with all this introduction, we are all happy about virtual thread, and we want to use virtual thread everywhere. We just want to drop all our usage of native threads, right? And actually, in reality, it is not like this. Okay, virtual thread are not going to replace completely native thread. They are another tool, and the point is that we need to understand and know the good and bad feature of this tool in order to use it in the right situation, in order to use it appropriately. So the main idea of this talk is to show actually where virtual thread falls short in with practical examples. So based on my experience, I'm providing some example of what can go possibly wrong with virtual thread and why you should use them everywhere, but only in a specific situation. So first of all, The first problem of virtual thread is that, as I said, the virtual thread are very good at waiting, so are very good when you perform I/O operation for I/O bound task. The problem there is that they are not that good for the CPU bound task, and for a couple of reasons. First of all, they are not preemptive, so when you use virtual thread, there's a lack of fairness, and I will demonstrate this with a quick example. And there is also a performance cost in managing the virtual thread, in mounting and unmounting the virtual thread on their carrier and all the machinery around this. Then one other problem is that, as I said, the virtual thread are a relatively new feature. They have been introduced, I think, in JDK 18 or maybe 19, but they are generally available and only with the latest JDK, only with the JDK 21. The result of this is that not only tools and library are ready to be used with virtual thread, and the two main problem here is that in some specific circumstances, it's not possible to unmount a virtual thread from its carrier. When this happens, we say that the virtual thread is pinned to its carrier. And the problem in this case is that if you perform a blocking operation on a virtual thread while it is pinned to its carrier, you are not only blocking the virtual thread, but as I said, in that case, the virtual thread cannot be unmounted. And this means that also the carrier will be blocked. So you are wasting a scarce resource in that case. You are blocking the carrier thread, which is something that you don't want. Okay, so there are a few situations where the virtual thread is pinned. The most common one is in synchronized block. Okay, so if you perform an I/O operation in a synchronized block, the virtual thread cannot be unmounted, and you are blocking also its carrier. A few libraries do this still, so they are if you use them, they are not using a tool that is not virtual threads friendly, and probably you even don't know. And another problem is with the use of thread local, but I will go deeper into this with an example later. And the last thing is that, as I said, by default, well, it's not only a default. You don't really have a choice. It's the only thing you can, the only way you can run virtual thread. They run on a fork join pool dedicated to them, and so you are not free. You are not allowed to choose your pool of carrier thread. Okay, there is only this fork join pool provided by the JDK, and you cannot access to it. Is something that is under the control of the JDK, and you cannot replace it. And I will try to demonstrate why this could be a problem in some cases, but also I will provide a very, very good example to demonstrate why the JDK architect took this decision, and how we learn it was the right decision in the hardest possible way. Okay. By the way, feel free to interrupt me in case you have questions.
So Mario,
yes.
there was a request to push the hide link of the toast message from your screen sharing.
To post
you
what?
Can do that.
To post what? Sorry.
I think it. I think it's the thing at the bottom where it says stop sharing.
Ah,
If you can move that. Oh yeah, hi. There we go. Okay,
okay,
great.
okay, okay,
All right,
okay.
thank you. Yeah.
Thanks. Okay, so let's try to evaluate all these points in deeper details. Okay, so my first point is that, as I said, virtual threads are not preemptive. Okay, so what happens normally with native thread is that they are under the control of the operating system, and it's up to the operating system to decide when a thread took too much of a CPU of a core, and it's time for that thread to be interrupted, and to give to another thread the possibility to do some work on the same core. Okay, so this is what normally happens with the native thread. Unfortunately, you cannot do this with the virtual thread. I mean, since they are not under the control of the operating system, they are not preemptive, and they will leave the CPU and leave the carrier only if and when they perform an blocking operation, and typically an IO operation. But if you have a completely CPU bound task, they will this will never happen. Okay, let me try to demonstrate this with a simple example. Okay, I'm hoping that you can read my code, that the font size is big enough. But if there is any problem, just please let me know. With this first example, what I'm doing here is performing the same CPU bound operation in parallel. Okay, as I said, my machine has 8 core, so I'm performing this operation 64 time in parallel on 64 different threads, and the operation that I'm performing is this CPU bound task, which is a very stupid task. It's just something that keeps the CPU busy, as I said. So I'm counting from 0 to 10 millions, and I'm doing this using a big integer just to put more load on the CPU. Okay, and as I said, I do this in parallel on 64 thread, and the only other characteristic of this example is that I can choose if I want to run this stuff on virtual threads or native threads. Okay, so the way how I'm doing this is that when a task has to be executed on a virtual thread, I simply do this, while when a task has to be executed on a native thread, I have a pool of native thread, okay, which reflect this daemon just to avoid keeping the CPU, the program alive, and then I execute this task on one of the thread provided by this pool. Okay, so this is the way how I'm switching between virtual and native thread. Okay, so let's try to give a run to this main. For the first time, I will run this with native thread that, as I said, are preemptive. Okay, meaning that they can be interrupted. Okay, what this stuff is printing is okay. The result for each and every thread is of course the same. They are counting from 0 to 10 millions. The threads has an ID from 0 to 63, and this the duration that the thread took to complete that CPU bound task in a millisecond. Okay, so you can see some stats here. The average was almost 3 seconds. And you see the minimum and maximum duration. But interesting thing is that all the duration are more or less the same, or are in practice distributed on a Gaussian around the average. Okay, so this is very typical. Why? Because all these 64 threads are competing to run their stuff on my 8 cores, and the operating system is giving a reasonably similar amount of time to all of them in order to make them progress more or less on the same time. Okay, so let's see what happens if I do exactly the same exercise but by using virtual thread. Okay, as I said, now virtual thread are not preemptive unless you don't do any IO bound operation, but I don't have any IO bound, any blocking operation in this program. So this means that once a virtual thread take the core, it will go up the end of the execution without never leaving it. Okay, and this is something that you can read from the results. So you can see that the first 8 thread took the CPU and performed the task, and then and only at that point that they leave the CPU one by one, and then you see another block of a thread. You see the gap between this and between this, and so and this goes on for 8 time. Okay, so this what I mean when I say that virtual threads are not preemptive, and of course, yes.
So yeah, Mario, Marian Varga has a comment here, and I think like your feedback, it says, I would say if you use a thread pool, that should already be a sign that virtual threads are not a good idea.
I'm not using a thread pool for virtual thread, by the way. So just to because as I said, the virtual threads are a very cheap resource to be created. So pooling them is an anti-pattern. Okay, I'm using a pool only for native thread, while for virtual thread I'm creating 64 of them.
And then Sebastian Bigel has a question here. Can virtual non-daemon threads block the JVM shutdown by pinning a platform thread?
No,
so.
virtual threads are all daemon by default.
Okay. He says, I don't think so, as it should use the common pool, which consists of daemon threads already. So
yes, exactly.
Okay.
Yes.
Cool.
Okay. The other thing that I want you to notice, okay, the mean duration is of course much faster than before, but if you remember also the average now is faster. Before it was 2.9 seconds, and now it's 1.9. Okay, and of course, why the average is faster? Because fairness has a cost, right? So if you want a fair execution, you have a more context switch between thread, and this fairness has a cost. So this is a totally unfair execution. But if it's okay for you to be totally unfair, then you have an high throughput if you want. Okay, so of course it's a trade-off. So this should demonstrate quite visually and easily what I mean when virtual threads are not preemptive. Okay, and again, could be okay for you, but typically it is. You want a fair execution of all your CPU bound tasks, so be aware of this. Okay. And also, as I said, the machinery used by virtual thread also has a cost. And in order to demonstrate this, I also have another example. Okay. now I created a more formal benchmark using JMH. Uh, exactly as before, I have the possibility to run this thing with either a virtual or native thread. I'm running this thing 100 times in parallel this time. Uh, this is more or less exactly what I did before, with the only difference that JMH offers you a facility to have a CPU bound task. So here I'm having it's similar to uh, what I did before, but without the need of creating my own method that consumes the CPU. I can just say to JMH, do something that consume 100 cycle of clock of my CPU. And I'm doing this in parallel exactly as before. Okay. And the result of the benchmark will be how much time 100 virtual or native thread will take to perform this execution till the end. So if I run this benchmark, as I said, this is a parametric benchmark, so the thing is executed twice with virtual thread and with native one. And as you can see, when you use the native thread, this thing goes much faster. Okay, and I tried to understand why. So and I created some flame graph to demonstrate this. So just to read the result that I found with that flame graph. Here, in reality, the actual work that the thread are doing is this instruction. Okay, this is the actual work done by the 100 threads, either virtual or native. So the 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 thing that we want to do is that we want to use to maximize, let's say, the execution of this, while all other execution is the overhead caused by the context switch and the management of the different 100 thread made in one case by the operating system mostly, and the other case by the JDK. Okay, so as I said, this consume CPU is the actual work that we are doing. Here I'm showing the flame graph demonstrating the execution with the native thread. And as you can see, almost the 22% of the time is taken, is spent doing some actual work, while all the remaining time is the time necessary to coordinate the native thread. Okay, so the 22% could seem a quite small value, but with virtual thread things goes much worse. As you can see, now we have just a little bit more than the 2%. So the actual work is only the 2%, while the other work is mostly made in these purple blocks, is mostly made to mount and unmount the virtual thread from their carrier. Okay, so just to be clear, this benchmark is really extreme, and it's something that I purposely made ad hoc to demonstrate the problem. Okay, I just want to emphasize the problem as much as I can. Normally, you are not in this situation, so here the task that I'm doing, this consume CPU, is very fast. It just takes 100 cycles of clock. Normally, you are not in this situation, so the proportion between the actual work and the overhead introduced by the management of virtual or native thread is much smaller. Okay, so it's not always that bad. I just wanted to emphasize the problem. But as you can see, in this case, there is an overhead that you may want to consider. Okay, I don't know if there are questions about this. Otherwise, I will move to the next problem. The next problem is about thread locals. So let me just recap what thread local are and what why they have been introduced, what are their main purpose. Okay, so what I wanted to do with this example is performing an operation on a database, and I can perform this operation on a database only if I have certain rights. Okay, but I don't want to pass the my rights level to all the call to down to the database call. I just want to say, okay, I at some point I figure out what are my rights level if I'm an admin or a guest, and I set this value on this principal that is the thread local, and so I set the value um, of the rights that I have in this thread local, and then I'm not obliged to pass this value down to the all the subsequent call. I can just access the database, but before doing so, I can read the right level from the thread local, and use that value and decide if I'm allowed or not to create a new database connection. Okay, so this is pretty simple, and this works with the native thread, but of course it works perfectly also with the virtual thread. Okay, so here I'm putting the code in the former slides at work by using two virtual threads. One is okay, they are labeled as authorized and not authorized, but one is performing the is calling the server with that second variable set to true, meaning that I have the admin rights, and the other is passing false, meaning that it has the guest rights in that point. Okay, and if I run this, it happens exactly what we expect, meaning that the virtual thread that is not authorized will get an exception, while the other thread, which is the authorized one, will be able to create a database connection and get a result. Okay, so this demonstrates that thread locals work seamlessly and perfectly also with native thread. Right? So everything is fine. What's the problem? Okay, the problem is that by design you may want to have many more virtual threads than native threads. This means that the thread local uh, 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 the memory taken by the thread local will grow very fast, and this is one problem with virtual thread. To overcome this problem, they introduced another data structure that is similar to thread local, but it's called scoped values. This scoped values is still in preview in JDK 21. It will be, I believe, almost for sure generally available with JDK 22, so in less than 2 months. The way this work is very similar to thread local. The what I'm doing here is that instead of setting a value on the thread local, I execute the thread in the scope of the scoped value. So before starting the thread, I associate to the thread a few value, and then I execute the thread with that value associated on it. So it's very, very similar. The main difference, and I believe it's a good improvement. Thread locals are mutable, meaning that once you start a thread, you can still change the value of that of the variable associated to a given thread, while scoped value are immutable, meaning that once you start a thread with a bound value for a variable, that value will be immutable for all the life of the thread, for all the execution. Okay, so in essence, the idea is that, okay, if you use virtual thread, there could be a memory problem, because you will have many virtual thread, and they each thread, basically each thread local, you can think to thread local as a hash map, and each key is a thread. Okay, so this means that the memory taken by thread local, if you use them with virtual thread, will grow very fast, and with scoped value you will basically resolve this problem. So you may think, okay, we will replace all thread locals with virtual thread, and we are done, with scoped variables, sorry, and we are done. Okay, that's true for the example that I demonstrated so far. But unfortunately, there are a few other use cases for thread local that are not so straightforward and are not covered with scoped value. Okay, the most relevant one, and this is something that many tools and library use, is using thread local as a thread safe object pool. Why they do so? Because it's easy to implement and use. So you put a resource that you want to pull into a thread local, meaning that only one thread at a time can use it, and you are done. And this is thread safe in the easiest possible way. And it's also easy because you don't need to set a specific life cycle. I mean, you don't need to say, okay, I'm using this resource, and then at some point, when I'm done using that resource, I need to put it back into the pool. This is not necessary, because the resource is still in the thread local. You are not taking it away from the thread local. You are getting from the thread local, but the resource is still there. You are the only thread that can use it in that moment, so it's thread safe. But you still don't have to put it back. The thread using that resource die, and then the resource remains there. Okay, and in this scenario, scoped values don't work at all. And this pattern, which again is very common, uh, works particularly bad with virtual threads. And of course, I also have an example to demonstrate this. Okay, so let's see what I'm doing here. I'm doing a task 500 times in parallel. As usual, I'm using um, 500 virtual threads, while if this is executed on native thread, I'm taking them from a pool. Okay, so in reality, I only have a number of thread equal to the number of processors of cores on my CPU. So I will have a pool of 8 native thread as usual. Okay, and the other the characteristic of the task that I perform in this example is that to execute this task, I need to allocate this expensive resource that creates an array of alpha billion bytes. Okay, so the thing is that if I don't do any pooling, each of the 500 execution will have to create on its own that expensive resource. So I will have 500 different instances created for that expensive resource. And indeed, if I try to run this in this situation, it will probably take more than 10 seconds, or since okay, it takes 12 seconds in this case, right? So this is the execution with native thread, but without using any pooling. Okay. Now let's try to enable some sort of pooling. The pooling that I'm using is this thing that is based on the thread local, and the way I'm using it is that I try to pull where I create it and I add to the pool, and otherwise I use it as it is. Okay, so this stuff is thread safe, but in reality, I only have 8 threads. So I have 500 execution executed on 8 thread that are provided by this executor. Okay, so this means that by enabling this pool, I'm creating that expensive resource just 8 times instead of 500s. And as you can see now, the execution is much faster because I'm using this pool, and the execution is much faster. Okay, now we learned how many tools use this thread local as an object pooling. Let's try to do the same with the virtual thread. The problem here is that, as I said, typically you don't pool virtual thread. This means that if you do so, the thread local pool is totally useless, because you will have anyway 500 entry in this thread local. So you have to create 500 expensive resource, regardless if they are pooled or not, because each and every virtual thread will have its entry into the thread local. And we are back basically to the 12-second execution that we had without any pooling. Okay. So if you think about it, in this case, we would like to have a thread local that doesn't have the virtual thread as key, but as the carrier of that virtual thread as key. And in that case, you will have once again the expensive resource to be created only 8 times, and we will take the advantage of this. Okay. In reality, in the JDK, there is no such a thing, or better, of course there is, but it's hidden. You cannot use it. It's this carrier thread local class, which is hidden, which is an internal JDK class. You are not supposed to use it for a good reason, but if we try anyway to enforce the usage of this thing via reflection, you will see that also with virtual thread, the execution is will be faster. Okay, why? Again, because now once again I'm creating the expensive resource only 8 times. And the reason why you cannot use it really is that it is extremely unsafe. The problem is that the main problem is that when virtual thread is performs a blocking operation. It is unmounted from its carrier, and when the blocking operation terminates, it is mounted again. But it is not said that it will be mounted on the same carrier thread. It could be mounted on a different carrier thread of the same pool, meaning that if this happens, I took a resource from a slot, from a bucket of a carrier thread, and then I do a blocking operation, and then I'm mounted from that carrier. Then when I'm restored, I will mount it on a different carrier, but I will be using a resource that it was meant to be created for a different carrier, for the first carrier. Okay, so this is why this thing is extremely dangerous and in essence wrong, and this is why this thing is not exposed to the end user. It's not something that you are supposed to use. Okay, so to cut a long story short, this pattern is very common, and unfortunately it works extremely bad with virtual thread. For instance, this problem has been reported by my colleague Francisco in the Jackson core. I guess most of you knows and use Jackson even indirectly, because all of us do serialization of JSON. There is no way to avoid it. So all of us use Jackson, and Jackson uses exactly this pattern. They have a thread local based pooling, and yes, we discovered this problem. We discussed this for a while with the maintainer of the project, and at some point I get tired of discussing this, and I provided my own fix. I created a pull request, a change that allows to plug your own pool implementation, so you can create your own friendly pool, thread friendly pool, meaning a pool that it doesn't use the thread local under the hood, and you can use this virtual thread friendly pool by injecting it with a new SPI, and this work all with virtual thread. So this feature has been merged a few months ago. Now it is available in Jackson from Jackson 2.16. So if you are using Jackson 2.16, you already have this feature. Okay, and just to be clear, the main problem when I created this fix, this patch, was that not replacing, not giving the possibility to replace the thread local pool with a different pool. The problem is that before my change, that resource managed by the thread local based pool didn't have any life cycle at all, while a proper pool did need a life cycle. So this new pool has just basically two operations: the acquire and the release one. And before, it was only doing the acquire, it was never doing the release, because with the thread local implementation it's not necessary. But now if you have a different pool implementation, you need the release. So again, the hardest part of this change was to create a life cycle for all the usage of this pooled resource. Okay, so this is what regards the thread local problem. And again, now Jackson since 2.16 has this the possibility to plug your own virtual thread pool. By default, in Jackson 2.16, we are still using the thread local based implementation, mostly for compatibility reason. Since Jackson 2.17 that will be out in the next month, the default will be using a virtual thread friendly pool. Okay, so this is to say that okay, now the problem is solved with Jackson, but we know that there are many other tools with this problem. So be aware that you may use a tool with this problem, and if you try to use it with virtual thread, you can basically not having any object pooling at all, which could be a performance problem. Okay, the last thing that I wanted to mention is the possibility of plugging your own carrier pool. As I said, this is not really possible, or again, it is possible by using with some X by using some internal API of the JDK that you are not supposed to use. And I did some experiment with this thing. And if you remember my last presentation last year, I have my own benchmark that is a game on Loom implementation based on virtual threads. And I tried to use different implementation. I tried to switch different carrier pool to check if I could create a more performing fork join, a more performing carrier pool, more performing than the default fork join for my benchmark, for my game of Loom. Okay, and in reality, I couldn't find any. I mean, as you can see from the number, the line in red, the native fork join virtual pool provided by the JDK largely outperform all other my naive implementation. So we're mostly happy, basically happy with this fork join pool for virtual thread. Okay, but in reality, why are we bothering trying to replace it if its performance are so good? For instance, we could have these needs in Quarkus. As I said, I work for Red Hat. I'm a Quarkus contributor, and yes, some of the example that I'm showing today are the result of the experiment that we did on Quarkus with virtual thread, especially this one. Okay, so what's the idea here? If you think about it, all framework based on an event loop like Quarkus or Netty, which also on which also Quarkus is based, they do something very simple. As you know, the mantra is that you don't block the event loop. So when you perform a blocking request, you perform it into a lambda expression, and then the event loop is able to serve other requests while the first one is blocked in its own blocking operation. Okay, and if you think about it, this is exactly what the virtual thread does. Okay, the event loop now is the same thing as the carrier thread, and when a virtual thread perform a blocking operation, now you don't. The only difference is that you don't have to put this operation into a lambda expression following the API of the event loop, but you can perform the blocking operation sequentially or apparently sequentially. And what the JDK does for you, it's exactly what you normally do with with an event loop. When you do a blocking operation, the virtual thread is removed from its carrier, and you give the possibility to another thread to move on. Okay, so they are exactly the same thing if you think about it. Okay, and now in Quarkus we have this experimental annotation that is called @run on virtual thread, and you are allowed to annotate a method with this annotation. And when you do so, the body of that method is executed inside a virtual thread, which is cool. What's the problem with this? The problem with this is that still Quarkus need an event loop to allocate all the tasks that it execute. Okay, so in essence, when we serve a request that runs on a virtual thread, we are obliged to do two additional context switch, one to jump from the carrier to the event loop, and then back when the response is ready. Okay, and so why we wanted to plug a different carrier pool other than the fork join pool provided out of the box by the Java virtual machine. Because if you think about it, as I said, the carrier pool and the event loop has exactly the same logic. Okay, so think about it. We could make the event loop to be itself the carrier pool, and by doing so, we could avoid this double thread switch while serving a request that executed on a virtual thread. Now, you don't have to jump from the carrier thread to the event loop because they are the same thing, they are the same thread, and you are saving two thread switches. And this is the reason why we wanted to experiment with this solution. And again, there is a way quite very hidden in the JDK to allow you to plug your own thread pool. Okay, in reality, this possibility was allowed since I believe the end of 2021, and then we removed it, and we found in the hardest possible way the reason why they removed it. So let me demonstrate this with my last example. Okay, so in this example, I'm doing exactly what I'm saying. I have this event loop that is typically a single thread. And then I create this event loop factory. And when I do so, I'm doing this by accessing in this ugly way that internal API to replace the carrier pool. Okay, so in essence, what I'm doing here is that now I'm replacing the carrier pool. The carrier pool for the virtual thread is no longer the fork join pool, but it is the event loop itself. While doing so, okay, then look what I try to do. I have two things doing exactly the same thing, one inside the event loop and one inside a virtual thread. They try to perform an operation while acquiring a lock. Okay, and then I have the main that is just the coordinator here. I acquire this lock first. I wait for both this thread to arrive to this point, and then I unlock this single lock, and then I expect that one of the two that is trying to perform this operation will be able to acquire a lock and move forward and arrive here. But as I wrote, this never happens, and this is the problem. If I run this, no, sorry, I'm running the wrong thing. If I run this, you will see that, okay, the main thread acquired the lock, and then it awaits the two thread to join, the virtual one and the native one. And both the virtual thread and the native thread that is also the event loop are trying to acquire the lock. The main releases the lock, so one of the two should take the lock, but it can't because I, in essence, created a deadlock. Okay, and the very, very bad, ugly thing is that normally you need two locks to create a deadlock, because you have a lock one that is hold by the thread one, and a second lock that is taken by the thread two, and then the thread two try to also take the lock one, and the thread one try to do the same with the lock two, and they are basically blocked waiting for each other. Okay, so typically you can have a deadlock, of course, but in all cases you need at least two locks to create a deadlock. Okay, what is really bad here is that I'm creating a deadlock with one single lock. Okay, and I tried to explain what's happening here. The problem is that now you have the carrier and the virtual thread trying to acquire the lock. Uh, the main does a busy waiting for both the carrier and the virtual thread to try to acquire the lock. But at that point, when the main unlock the lock, none of the two other thread can take it. The virtual thread cannot take it because its carrier, it cannot make any progress because its carrier it's also cannot make any progress because is that locked on the same lock on which the virtual thread is trying to make any progress. Okay, so in reality, what happened is that I'm showing you with the simplest possible way the problem that we found in Quarkus. As you can imagine, this problem, when I tried the solution that I sketched here, uh, we ended up with some locks. We didn't understand what was going on, and it was very hard to figure out where the problem was. And then once we have understood, I created this synthetic example showing the problem. But as you can imagine, it has been quite hard to reverse engineering the problem and created an isolated reproducer. Well, not creating the isolated reproducer, that was relatively easy, but understanding how to do this, understanding what was going on. Okay, so in essence, with this talk, I wanted to bring my experience with virtual thread, them showing all the experiment that I did and we are still doing. And yeah, the key takeaway of this whole discussion is that the virtual thread are not a complete drop-in replacement of a native thread. They have different features, they have different characteristic, and to know both in order to figure out which is the best fit for the problem that you have. And with this, I concluded my talk. If you want to learn more about all the experiment that we are doing with virtual threads in Quarkus, you can follow this link. There is very updated blog post when we are gathering all the experiences that we are doing with virtual thread. It's mostly maintained by my colleague Clement Escoffier, but many of the Quarkus team are collaborating to this. And that's all I have.
All right, Mario, this was awesome. Let's everybody thank Mario. I'm acting as if we're actually in person somewhere. But yeah, at the moment, there was one comment earlier. Let's see if I can find it there. Had to do with profilers. Yeah. So Francesco said, and attaching profilers, virtual threads have a scalability issue too. So, and then just getting back to where people were checking in, we left off. So, MK Tan is from Malaysia.
Hi.
So let's see.
Hi everyone. Thanks
From Chakuka, if
for
I
joining.
pronounced that correctly, from Nigeria. Thanks for coming in. And then from Maodo from Senegal. And
Nice.
then I've seen Gary before in other sessions from Missouri. So and then Vincent from France. And yeah, let's see.
Nice.
And I think that's it. Let's see. Yeah.
Okay. So
Yeah, that's it. And then, Sebastian said, thank you very much for this session. With helpful information about virtual threads and how
yeah,
to
that last example, I must admit, was really mind blowing. And again, we had that time trying to understand what was going on there. Yes.
So yeah, so with that, the next session is what's new in CDI4, which of course will be coming out in Jakarta EE11 later this year. So looking forward to seeing what's going on there. So, all right. So with that, thank you, everyone. Like I said earlier today, it's been my pleasure moderating these sessions, these last 4 days, and enjoy the rest of the conference.
Thanks a lot. Have a nice day.
Okay. Take care.
Bye.